Great. Nuclear chemistry today. Hot in here, you think? Okay. Better. Okay. For the first time, we'll be talking about the nucleus this semester. So far, everything has been about electrons and stuff, right? Chemical reactions are about electrons, intermolecular forces, and so on and so forth. This is the first and the only time we'll be delving into the heart of the atom, which is the nucleus. What is the nucleus made of? What two particles? Protons and neutrons. P plus, neutrons and 0. Protons are positively charged, neutrons are neutral, 0 charge. Together they're called nucleons, right? And so a nucleus has a bunch of protons and a bunch of neutrons in it. Roughly speaking, they should be half-half, with neutrons a little more than protons. So the number of neutrons and the number of protons are about the same, but this one is technically higher. You have more neutrons to hold the nucleus together. If you sway too far in either direction, if you have too many protons, the nucleus is unstable and it will break up into smaller nuclei with more stable configurations. And same thing happens if you have too many nuclei. Okay? So this actually forms one of the strategies for breaking up an atom. Suppose you have a really heavy nucleus and you want to break it up. Well, make it unstable by shooting neutrons into it. If you take a heavy nucleus and you shoot some neutrons into it, it will keep absorbing those neutrons that you're putting into it. And at some point, the ratio is going to be so skewed that you'll have too many neutrons, and that's a problem. And so the nucleus will break up. Nuclear fission. This is what happens in atomic bombs. You have a very delicate, high-mass nucleus that's like, give me one more neutron, I'll break kind of situation. And so you have all that material, all that nuclear material in the bomb, and then there's a secondary part of the bomb that is a neutron source. Okay? So once you remove, very roughly speaking, the barrier between the neutron source and your delicately, almost breakable nucleus, give it one more neutron and it will break up, releasing a tremendous amount of energy. That's the principle behind a nuclear bomb. We'll discuss that in more detail later down in this chapter. When a nucleus breaks up, when a nucleus breaks up, it can break up, so you have a parent nucleus that breaks up into a daughter nucleus, right? It's a heavy, slightly lighter. And it does this by emitting some small particles, right? Sometimes a nucleus can literally break in half, and so you get two very light daughter nuclei. But often what happens is you have a heavy nucleus that breaks up into a slightly lighter nucleus, and chips away at the mass. So small particles are given off, plus some particles. This is nuclear decay, right? Because a heavy thing is decaying into a smaller thing and a bunch of small particles. This is decay. The opposite is absorption or fusion, where the opposite happens. You have a particle, a small particle, that gets absorbed into some kind of a target nucleus to give a new nucleus. I guess you can call this daughter and this parent, but not really, because here the parent is forming the daughter. You can't have the daughter forming the parent, right? So this is called the target, and that's like, this is a transmutated nucleus. It just means that it has been changed. Some common terminology. Okay, so the first thing is decay. The second thing, despite the complex terms, is literally just the opposite, absorption or fusion. In the same way, decay can be called fission. Fission is breaking up, fusion is coming together. Okay. Two principles will guide us through this chapter. One is that mass is conserved. Very much true, with a hint of falsehood there, but mass is mostly conserved. That's one. And charge is conserved. So the two things that should balance out, you know how in a chemical reaction, the number of atoms should balance out on each side? That's our guiding principle for balancing chemical reactions. In balancing nuclear reactions, our two guiding principles are the mass should balance on each side and the charge should balance on each side. So that's the idea. So conserved quantities are mass with an asterisk, because mass is actually slightly lost or slightly gained, but that's okay. Mostly conserved, and charge. Okay, we'll use these mass and charge conservation when we're balancing nuclear reactions in a bit. Let's make a quick list of common particles that you see pop up, absorbed or released in nuclear reactions. The first one is called alpha. And alpha particle is just the nucleus of a helium atom. How many protons are there in helium? 2. And how many, what's the mass of helium? 4, right? So that's a helium particle. You've seen this notation before, right? We've done this before. Atomic number on the top, mass number on, atomic number on the bottom, mass number on the top. So this is an alpha particle. Similarly, there's a beta particle. A beta particle is just an electron. What is the mass of an electron compared to a proton? What's heavier, protons or electrons? Protons are heavier, much heavier. So electrons are much lighter. So light that compared to a proton, you can call its mass 0. And what's the charge on an electron? -1. 2 technically stands for atomic number, right? Number of protons. But for the purposes of this chapter, imagine that to be the charge, right? So if you have 2 protons, you have +2 charge. If you have an electron, that's a -1 charge. So that's the nuclear symbol of an electron, -1, 0. Then there's gamma particle. A gamma particle is a photon. Photons make up light. Photons are famously massless. They have 0 mass. They actually have 0 mass and also 0 charge. They carry energy, but they don't have a charge and they don't have a mass. Very weird, right? You would expect something that doesn't have mass to not exist. There are things that exist without mass. And that's a gamma particle. Then there is neutron. What's the mass of a neutron compared to a proton? About the same, 1, yep. And what's the charge on a neutron? 0. It's neutral. And then there's this exotic particle that you haven't seen before. Electrons are negative. There is a positive cousin of the electron. Looks and behaves exactly like the electron, same size, same everything, except that its charge is positive. Think of it as beta plus particle. And its symbol is 0 plus 1. This is called a positron. If you have ever gone to a medical facility for a PET scan, positrons are bombarded at your body, and then you can get an image out of that. Positron emission tomography? I don't know, something. But it involves shooting positrons at your body to get an image. A little bit harmful, but not too much. But so are X-rays, right? X-rays are harmful, but you have to weigh the pros and cons. Okay, so these are the main particles that you should keep in mind. There's also a particle called a neutrino. Yes, neutrino. Neutrino is denoted by, I think, mu, if I'm not wrong. And neutrinos have very little mass and no charge, if I'm not mistaken. Yeah, neutrino. There's a whole zoo, just like there's a periodic table of elements, right? There's 118 flavors of elements that you can get, 118 flavors of atoms. There's a whole zoo, there's a whole periodic table of subatomic particles, particles that are smaller than an atom. That's called the Standard Model. You can look it up on Google. There's a whole periodic table zoo for the little guys. And these are only some of the players. And there's like bosons and fermions and like charm. There's quarks up top, top, bottom, charm, strange. These are all real names. Tinier than atom particles. And the whole field of physics that studies these things is called particle physics, because these are particles. Okay, so keep that in mind. Remember all of this. All right, now let's balance some nuclear reactions. Everybody good with this? Okay. Suppose you're looking at an atom of iron. Iron is 26 protons, and double that, 52. Increase it a little more, 54. 54 is a plausible, I'm just making up these numbers, but you see what I'm doing? I'm doubling it and then making it a little bigger, because that's usually the range of neutrons. Okay, so suppose you have iron, and iron decays, so that you would call this iron 54. See, the only number that you specify is the mass number, because that's the ambiguous number. If you say it's iron, then this number is fixed, it's 26. You can't change that. But because of isotopes, because the number of neutrons are not unique, you can have the same element with different number of neutrons. You have to specify what the mass number is. So often in questions, you'll see iron 54 decays by alpha emission or something. So 54 stands for the top number. So let's say the question says iron 54 decays by alpha emission. So it decays by alpha emission. So there's an alpha particle on the other side, 2, 4. Determine the daughter nucleus. Let me write that question up here. Alpha emission. Determine the daughter nucleus. So, in addition to the alpha particle that's emitted, emitted particles appear on the right-hand side, absorbed particles appear on the left-hand side. Right? Emit right, absorb left. In addition to this, you get some leftover daughter nucleus, X. If we can figure out the bottom number and the top number on this X, then we'll know the identity of this nucleus X. So remember, the masses should add up on both sides, and the charges should add up on both sides. What do the bottom numbers relate to? Charge or mass? What's 26 here? 26, this is a charge on an iron nucleus, right? So since if the charges need to be balanced, then the bottom numbers need to be balanced, and if the masses need to be balanced, then the top numbers need to be balanced, right? So the only thing that you want to do when you're balancing nuclear reactions is that make sure the bottom numbers add up and make sure that the top numbers add up. That's all it is. That's the game. So what would be here? 24, excellent. And up here, 50. Look up a periodic table, see what element corresponds to atomic number 24. Let's see. 24 should be chromium nickel? Nickel, I don't know. Does anyone have a periodic table?
Yeah.
Nickel?
Oh no, it's chromium.
Chromium, Cr? Oh. Is nickel 26?
Yeah, it's chromium. Nickel is
28. Can you just go from 20 to like 30 so I can remember? What's 20?
So 20 is calcium.
Uh-huh.
Then scandium.
Yeah.
Then titanium.
Uh-huh.
Then vanadium.
Okay.
Then chromium. Then magnesium, iron, cobalt, nickel,
Got
copper,
it.
zinc.
Thank you. Thank you. So this is chromium. Chromium, what would you call it? Chromium 24 or chromium 50? Chromium 50. That's the daughter nucleus. Great. And now you can imagine all sorts of questions in the same format. Here's another one. Iron 54 decays to, let's see. Decays to iron 53. What kind of a decay is this? What kind of decay? Yes. Neutron decay. Let's see how that works. Iron 54, 26, 54. This decays to iron 53, 26. So what is the mystery piece? 1 and 0, exactly. What's 1 and 0? If it's 0, you can't look it up in the periodic table. So it has to be a particle in the table. What particle has 1, 0? Neutron. Neutron is released, so this is neutron emission decay. Okay, here's another one for you. Identify the nucleus that decays to iron 53 by 2 alpha emissions. Take 5 and figure that out. What nucleus decays to iron 53 by 2 alpha emissions?
That's an alpha, right?
Hmm?
Is that alpha emission?
Yes, alpha emission. Right, that's the setup. Two alpha emissions, so 2 alpha particles get produced. Now tell me the numbers on the other thing. Anyone for the bottom number? 30, excellent. 26, and then there's 2 copies of 2's on the bottom. So that's 4 plus 26, 30. And the top number? 61. Yep. What atom would that be? Zinc. And how would I call it? Zinc 61. Excellent. So it's a very simple numbers game. Top numbers add up and the bottom numbers add up. Yes.
So I have a question just for clarity. So is the alpha particle always going to be helium, or can alpha particle be like a different other element?
That's the definition of alpha particle. It's always going to be,
Helium?
yeah. 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 The reason why we have 2 different names for the same nucleus, alpha particle and the helium nucleus, is because the nuclear radiation, the alpha nuclear radiation, was discovered first before it was understood what alpha particles are made of, right? So they had this nuclear emission and they were like, okay, let's call it something alpha. Alpha because it was the first nuclear emission they discovered, scientists discovered, so it was alpha. These are chronological terms, I think. Alpha was the first one, beta was the second one, gamma was the third one. And then they were like, oh, alpha is nothing but a helium nucleus. Beta is nothing but an electron, and so on. Yeah. Historical artifact. Okay, let me give you one more, and then we can move on. Okay. A mystery nucleus decays to iron 53 by simultaneous alpha emission and beta capture. Identify the mystery nucleus. Where would this beta particle appear? Left-hand side or the right-hand side? Left. Capture is absorption, right? Wow, okay. All right, tell me, what do I put here? Electron, beta particle, yep. -1, 0, and what else? Some X, great. Here, iron, 53 and 26, excellent. And helium. Great. What's this number? Let's see, 27. And so 27 minus 1 would be 26. 29, you want to go overboard. If in doubt, just set up the algebra. Call this x. X minus 1 should be equal to 26 plus 2. Will give you 29. Great. And the top number? 57. What element are we talking about? Copper. So the mystery nucleus is copper 57, exactly. Okay. All right. Let's move on to something simpler, which is something I should have done first. But I didn't because you've seen it before. Suppose you have something like this. This is a full atom. Suppose we're looking at everything, not just the nucleus, but also the electrons, right? Tell me how many protons you have here, how many neutrons you have here, and how many electrons you have here. Start with protons. How many? 26. How many neutrons? 28, top minus bottom, right? That's what neutron is. This number is protons and neutrons together. This is just protons. So if you want to isolate neutrons, top minus bottom, you said 28. Okay. And what about electrons? 29. Are electrons missing or excess? Missing. So normally they would be 26. Yeah, so 3 missing, 23. Excellent. If this was Fe3 minus, how many electrons would you have? 29. Okay. Okay. That's it. That's all. And you can, like in Alex and in other questions, you can have like various. Yes.
Wait, so if we're told to say how many electrons, protons, and neutrons we have, the protons are always equal to the
Atomic number?
electrons as
Correct. Correct. Yeah. This thing here only pertains to electrons, charge, because that comes from general chemistry, not nuclear chemistry. Okay. And some qualitative stuff. You have the three kinds of emissions, right? Alpha, beta, gamma. Alpha has the least penetrating power. Beta has the next highest penetrating power, followed by gamma. Which means if you have like a big chunk of material and you shoot alpha particles at it, it will only travel a very small distance and then come to a stop. Alpha particles will travel a longer distance before coming to a stop, and gamma particles will travel a much larger distance before coming to a stop. Gamma is so hard to draw. Not draw, right? Because if that's gamma, then what's mu? I don't know. Okay. This calls for an inappropriate joke relating to alpha males, and I'll leave it to your imagination. Okay. All right. Not my original joke. I saw it somewhere. Okay. The last part of this chapter is kinetics, nuclear decay kinetics. How fast do nuclear decay reactions happen? We've seen chemical kinetics before, right? Zeroth order reactions, first order, second order. Good news, we're not going to study anything new here. All nuclear decay reactions are first order kinetics. So all the first order equations from chemical kinetics chapter apply here, nothing new. As a reminder, this was the first order reaction equation. N equals N naught e to the minus kT. In chemical kinetics, we might have had A, concentration of A, right? I'm just replacing that with N here, N for nucleus. N could stand for number of nuclei, or it could stand for, I don't know, some multiple of number of nuclei, whatever, something. There is another variation on this equation, which goes A equals A naught e to the minus kT, where A stands for activity. Right. So broadly speaking, the thing to remember is this is first order kinetics, N for nucleus, and if a question involves activity, it's the same thing, just put in A for activity. The reason why both of these equations, well, this one works because the kinetics is first order, and the same equation holds true for activity because activity is proportional to the number of nuclei. A is proportional to N. If I wrote this in a slightly different way, you'll see why that works. N over N naught is e to the minus kT. And I'm saying A is proportional to N, which means, what does proportionality mean? Same ratios, right? So A over A naught would be the same as N over N naught. So I can write A over A naught, and you'll get the same equation again in terms of A's. You don't have to worry about that, just saying where it comes from. Okay, let's do some basic questions. Oh, also remember that the T half is connected to K as follows. Ln2 over K. Again, nothing new from chemical kinetics, if you remember. Okay, here's something nice now. Suppose you have 200 grams. Suppose the US has, I don't know, 10,000 kilograms of uranium in its arsenal. If you add up all the uranium that we have in our weapons and stuff, let's say it's 10,000 kilograms. I'm going to make up a half-life. If the half-life is 7 years, not true, but let's pretend it is. Then 2 parts. A, how much uranium remains "21 years from now." And part B, how much uranium has decayed in 21 years. This is a chemical kinetics question. You can use these equations to answer it, but there's an easier way. Do you see a curious relationship between 7 and 21? Yeah. How many half-lives is 21 years? 3 half-lives. What happens after the first half-life? What amount of uranium do you have? 5,000, because it halves, right? Good. Give it another half-life. 2,500. Another half-life. 1,250. That's it. That's the answer. So A, take your 10,000, wait a half-life, get 5,000, wait a half-life, you get 2,500, 1, 2, and 1 more, 1,250. This is an extreme example, but countries that have nuclear weapons have to keep refining and producing more and more uranium because it naturally decays, right? So the arms war, the arms race is never, the nuclear race is never over. It's slowly creeping along because you have to keep up. Yes? Exactly, then you would use this equation here. And we'll do a question like that. B is related to this. I wanted to give you both A and B because the wording can throw you off. Half-life pertains to how much is left, not how much is used up, right? That's some important distinction. So 1,250 remains. So how much was used up from here to how much has decayed from here to there? Exactly. Initial minus how much remains, 750 kilograms. Okay. Oh yeah? 8,750? I'm telling you, arithmetic is my downfall. I can never do this. I saw this meme recently. It goes, I've got devastating news. 550 divided by 2 is not 225. I feel like that meme applies to me. Because I would expect 550 divided by 2, of course it's 225. It's not. Right? Half of 50 is 25, so it should work. No, doesn't. Okay. That was for me. 8750. Great. Yes, now to answer your question, what if you don't have convenient values like this, then you just use these equations. And for good measure, let's do a question with activity because it's the same if it was n. Okay. Let's see. A nuclear waste facility has an activity of, let's just make up some number, 120. If the half-life of the spent nuclear fuel kept at this facility is, give me some number, how many years? 12? 12 years. Determine the activity in 20 years. Not a multiple of 12. In 20 years. Let's say that's your part A. Same question could be asked in a slightly different way. Determine the percent reduction in activity in 20 years. Okay. Activity has some units. I forget. Look it up in your textbook. Becquerel, Curie, something. I don't know. Some units. Okay, A. So this is an activity question. We don't have nice multiples. If this was 24, the question would be easier. It's 20, so we're just going to go ahead with our equation. A over A naught equals e to the minus kt, where k is ln 2 divided by half-life, which is 12. Great. Okay, give me the numbers. Which of these values do we already know? What's this 120 here? A or A naught? A. No, sorry, A naught. Because that's what you start with, right? A0 is what you start with. A is at time t, which here is 20 years. Yep, all good. It's been a while since we looked at that chapter. Okay, so A, I don't know. A naught is 120. E to the minus k is that mess. ln 2 divided by 12 times time is 20 years. Let's say this comes out to some number. And so A would be 120 times that number. And that's it. Okay. What's percentage reduction? It's how much the activity has changed divided by, it's Reduction or increase percent is always change divided by initial times 100, right? Change, it was higher at first, and then it decreased because activity goes down as samples decay. And so it would be A minus A naught divided by initial, which is A naught. Sorry, the other way around. A naught minus A. Initial minus the final value divided by A naught times 100. Okay. We can simplify this or not. You don't have to simplify. Let's plug in our values. A naught is 120. A is 120 times this mess divided by the initial 120 times 100. Can you simplify this any further? What's common in both of these terms? $120, right? What's left here? A 1. What's left here? Whatever that number was, divided by 120 times 100. So these numbers cancel out. And so the percentage change is 1 minus whatever that number was times 100. It'd look better if we actually found what the number hash was. That's fine. Yeah. You can imagine what it is. Notice something curious. The 120s cancel. 120 was the activity, right? The initial activity. So the same question could have been asked without the 120 given to you for part B. You could simply be given a question as follows. A nuclear facility, blah, 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 has spent fuel. If the half-life of the spent fuel is 12 years, determine the percentage reduction in activity in 20 years. In that case, if you didn't have 120, how would you do that? Let's see. What I want is A naught minus A over A naught times 100, correct? Can you simplify this in a different way? Can you split up this fraction into two pieces? You can, right? Numerator is always allowed to split, not the denominator. So this is A naught over A naught minus A over A naught times 100. A naught over A naught is just 1. So all we need to figure out this percentage is this guy, A over A naught. You don't need A separately, you don't need A naught separately. You just need the ratio of A to A naught. Going back to the first order equation, what is A over A naught? E to the minus kt. So this would be 1 minus e to the minus kt times 100. This is the percentage reduction. And you see it doesn't depend on A naught at all. It only depends on K and T. Yeah. I'm just giving you like the general equation in terms of variables, but if you had the numbers, if you were able to find this number and you have the initial number, then it's just a simple percentage problem. Yes?
If it's negative, what do we do?
You won't get a negative number. Because this number over here will always be less than 1. So 1 minus a smaller number will always be positive.
But don't you multiply by the 120 to get A?
In this formula?
For like the first for A, to find A, you do the e to the negative.
Yeah, yeah.
A multiplied by 120.
This still is never a negative number. This is always a positive number.
So when you use it for B, you're just using that word.
Yeah. That's the point. You skip A naught. See, none of that information is given. If for a question like this, you'd simply be given something like half-life is 12 years. Determine percentage decrease in activity in 20 years. That's all the information you have. You don't have any A's, you don't have any A naughts. 2 pieces of information, T half and T. T half would help you determine K. T would go in here.
No, I'm saying when you're given the A and everything, like the original problem.
The original problem.
So if it's A initial, that's initial, right? Zero.
The A initial is 120.
Yeah, so the A initial minus A could be minus A over A initial, right?
Yes.
So it'd be 1 minus whatever you found for A.
120 minus whatever you got for A, divided by 120.
Yeah, but didn't you say you canceled it out to make it 1?
Sure. If you want to simplify it like that, then it would be 1 minus A over A naught.
Oh, so the over A now still stays. Okay.
It still stays, yeah, it's not going anywhere. Yeah. Any other questions? That's it, that's the chapter. Top numbers add up, bottom numbers add up, and nuclear decay reactions are first order. That's all it is. Oh, of course, and then you have to remember that table of subatomic particles, alpha, beta, gamma. Okay. What time is it? Yes,
So I know today's the last recitation, right?
correct.
And will there be any review
Yes.
session for the final?
Yeah. Yeah.
Okay.
And I'm hoping for up to 2 reviews before the final, yeah. And I'll do that after I meet with the professor and come up with a strategy. Yeah. I feel like an in-person will not work for everybody. 'Cause
Agreed.
yeah, we'll do virtual. Okay, any other questions? We're done with Chem 2. I've covered every chapter, right? There's no chapter that I'm missing on. Thermodynamics is done, kinetics is done. Okay, so the material is covered. I owe you 2 reviews. And 2 more things before we leave. There is 2 review things that you need to do. One for the Department of Chemistry. I'll send it out via an email today. They use that survey to decide on hiring next semester. That's one. And I have a Rate My Professor. So if you liked this, then feel free to review me on Rate My Professor. Yeah, just look up my name. That's it. I don't need to write anything. Thank you. See, you guys are the best. I forgot attendance. You already took attendance, passed it around, and gave it back. Very nice. Okay, so I'll give you both links for the Rate My Professor and the departmental survey. It was my pleasure having you guys this semester. Wonderful class, and I hope to see you around.
Thank you.
No problem.